So let's get started with this test review. Number 1 reads, which of the following situations is not possible? A body has an instantaneous velocity of 0 and non-zero acceleration. What that means is that our acceleration is just some number, and we're looking for some instant moment where the velocity is 0. We know that that's true because that happens in freefall. When an object is thrown into the air, at the very peak of the motion, the velocity is 0, although the vertical acceleration is negative 9.8 meters per second squared. So that would be incorrect. B, a body travels with a positive velocity and a positive acceleration. Yes, that is possible. Letter B just describes an object that's moving towards the right and is speeding up. Remember that when the direction of the velocity and the acceleration are the same, an object speeds up. B would not be an answer because that situation is possible. Letter C, a body travels with a positive velocity and a negative acceleration. Well, this just means that an object is moving towards the right because its velocity is positive, but since the acceleration is negative, this object is just slowing down. Since that is a valid scenario, letter C cannot be our answer. That leaves us with letter D. A body travels with a constant velocity and a time-varying acceleration. Not only does this body have an acceleration, it varies. The very definition of acceleration is the change in velocity over time. This definition cannot hold in this scenario because letter D claims to have a constant velocity. So there's a mismatch here. Therefore, letter D is not possible and is therefore our answer. Number 2, starting from rest, a particle is accelerated at a constant rate of 5 meters per second squared. Which of the following statements accurately describes the motion of the particle? A, the particle travels 5 meters during each second. That is not true. The definition of acceleration is the rate of change of velocity. The particle has a constant speed of 5. That is also incorrect because velocity is changing if we have an acceleration present. The velocity of the particle increases by 5 meters per second during each second. That is correct. Letter D, the acceleration of the particle increases by 5 meters per second squared during each second. That is not correct. Letter C matches the definition of the acceleration, so we are going with that one. Number 3, a fast llama walks 12 kilometers north, then 16 kilometers east. The journey takes him 2 hours. Determine the llama's average velocity. Well, average velocity is just displacement divided by the time. Well, I know this takes 2 hours, but I need to find this displacement. Let's draw a quick sketch. The llama walks 12 kilometers to the north and then goes 16 towards the east. The displacement would be described by the resultant of this vector sum. I'll label it C. So in order to figure out what C is, we just have to perform the Pythagorean theorem. So we can follow C squared equals A squared plus B squared. And you can continue with that process. Another way to think about it is that we can identify this as a special right triangle, specifically a Pythagorean triple. The legs of the triangle follow the order of 3, 4, which therefore means my hypotenuse is 5. The reason why I know that this is a Pythagorean triple is because I can multiply all sides of this triangle by the same number and achieve the 12 and 16. I know that 3 times 4 is going to give me 12. Therefore, I have to multiply the other side by 4. And that is going to give me 16. Therefore, when I multiply the hypotenuse 5 by 4, it's going to give me a value of 20. This is a Pythagorean triple. Therefore, my displacement is 20. When I divide by 2 hours, I'm going to get 10 kilometers per hour. And that's going to be letter D. Number 4, an elevator is moving upward with a speed of 11 meters per second. 3 seconds later, the elevator is still moving upward, but its speed has been reduced to 5 meters per second. What is the average acceleration of the elevator during the 3-second interval? Let's identify what we're given. We're given an initial velocity of 11, we're given a final velocity of 5, and a time interval. That matches up with the definition of the average acceleration, which is the change of velocity over the change in time. We can expand this to be the final velocity minus the initial over this time interval. The final velocity is 5 meters per second. The initial velocity is 11, and the time interval is 3 seconds. Simplifying, 5 minus 11 is negative 6 meters per second divided by 3 seconds, and that's going to give me negative 2 meters per second squared. The magnitude of the acceleration is 2 meters per second squared, and the negative sign indicates that it is directed downward. So we're going to get letter B. Number 5 reads, A tennis ball approaches a tennis racket at 32 meters per second. The tennis ball rebounds in the opposite direction at 24 meters per second. The tennis ball is in contact with the racket for 0.1 seconds. What is the acceleration of the ball while it is in contact with the racket? Here, let us identify our knowns and unknown quantities. I know that the initial velocity of this tennis ball is 32. I'm going to draw a picture. I'm going to say that this is the tennis racket and that the ball is initially approaching it towards the left, where left is negative, right is positive, and this is the x direction. Therefore, I can write that the initial horizontal velocity is negative 32 meters per second. Then it's going to rebound in the opposite direction at 24. That means my final velocity is 24 meters per second, and that's positive. The ball is in contact for that amount of time, so my delta t is going to be 0.1 seconds. And I'm looking for the acceleration. Since I have my final, my initial, and the time, I can use the same acceleration as number 4. My final velocity minus my initial divided by the time. My final velocity is positive 24 meters per second minus my initial, and that is negative 32 meters per second. All of that divided by 0.1 seconds. Since I have minus, is going to turn to plus. So I'm going to add 24 and 32, and that's going to give me 56 meters per second divided by 0.1 seconds, and that's going to result in 560 meters per second squared. So I will get letter C for number 5. Number 6 reads, a fighter jet lands on an aircraft carrier at a velocity v. The jet requires a distance d to stop on the aircraft carrier. How long does it take the jet to stop after it lands? Let's go ahead and create some knowns and unknowns. So I know that the initial velocity is just v. It requires this distance d to stop. So this displacement, we're going to call it capital D. And I know that the final velocity is 0. And here it's asking me for time. How long does it take the jet to stop after it lands? Since I don't have any numbers, I need to find a symbolic representation that connects all of these knowns and unknown variables. There's actually an acceleration equation that can help simplify all of this. And it looks like this. Displacement equals 1/2 the initial velocity plus the final velocity multiplied by the change in time. We did not talk about this equation, nor is it on your formula sheet for the AP exam, but this is an equation that is good to know because of situations like this. The reason why I can use this is because I'm looking for an expression for the time, and I know my final, I know my initial, and I know my displacement. So I'm going to substitute these values in, and I'm going to solve for delta t. So my delta x is just capital D equals 1/2 of VI, which is just V. VF is 0, so it just disappears. And then I'm multiplying by the change in time. So to solve for delta t, I'm going to multiply both sides by 2. So I'm going to get 2 times the displacement equals V times delta t. And I'm going to divide by V. And this is going to give me 2D over V, which is letter D. It is possible to use the original 3 kinematic equations of constant acceleration motion, but it's going to take a bit more work because you're going to have to perform a substitution using one equation into another, and it'll get a little bit messy, but it's still possible to do that. However, it's worth knowing this equation because it can help simplify some situations just like this one. So let's say you didn't know about this equation. How would you solve it then? Well, let's take a look. If I'm going to use any of the big 3 kinematic equations, all of those have acceleration terms in them. If you notice, in this problem, I have nothing in my knowns and unknowns about acceleration. So what this means is that I need to make a substitution in some way. Let me use this formula so that way we can figure out what the acceleration is. So I know that my final velocity is 0, and I can move across my Vxi. So that way it'll be negative Vxi equals to Ax times delta t. Well, I can divide by the time. So that way I have an expression for my Ax. So my horizontal acceleration would just be negative V over delta t. I can use this expression in another formula and then solve for the time. I cannot plug it into this equation because everything's just going to simplify out. I need to plug it into a separate equation. And the one I'm going to use for that is this one. Okay, so let's go ahead and plug in the values that I have here as well as this expression. So, and remember, my goal is to solve for the delta t. Displacement is capital D, Vxi is V, my delta t stays the same, plus 1/2, and I'm going to get negative Vi over delta t multiplied by delta t squared. Well, what's going to happen is that one of these delta t's is going to cancel, and let's rewrite what we have. D is going to equal v times delta t minus half vi times delta t. Let's change this vi to just a v. Okay, so now we're getting somewhere. Here's one thing I can do. Let me get rid of this 1/2 just by multiplying by 2 on both sides. So I'm going to get 2d equals 2v delta t minus v delta t. Well, what I have on the right-hand side are just like terms. 2v delta t minus just 1v delta t, that's just 1v delta t. So what I'm going to get is 2d equals to just v times delta t. And then to solve for the time, I divide by v once again, and I get the exact same equation as before. So this just proves to you that letter D is our correct answer. But if you're going to use the big three equations like I mentioned before, it's just going to be a bit more work. But the first equation I showed you is kind of a lifesaver in this situation. And you know that you can use that equation when you're only given the initial and the final velocities, as well as the displacement and time. Nothing about acceleration. That's when that brand new equation I showed you can fill in. And remember, that equation is delta x equals half vi plus b vf times delta t. Number 7, Johann just goes and throws his physics book in the air at speed v. He finds that the book reaches a maximum height of h. How high would the book go if he instead were able to throw the book upwards with a speed of 4v? Now, whenever we're given problems like this, we need to set up our knowns and unknowns. So in this situation, I know that the physics book is being thrown into the air at a certain speed. So I know that the vertical acceleration is negative g. The initial vertical velocity is just v, and the final position is at a height h. That means my initial height, I'm going to declare it to be 0. My goal is to figure out what this new height would be if I were to adjust the initial speed to being 4 times the original velocity. Again, we have no numbers, so here's what we do. First, you need to find a relationship that combines all of my knowns and unknowns. Actually, before we do that, there's another idea that we need to incorporate, another concept. We're talking about the maximum height. What we find at the maximum height is that the final velocity, the final vertical velocity, is 0 meters per second. So that's another concept that we can apply to the scenario. And that is actually going to lead us to the equation that we're going to use to describe the motion. The equation is as follows. So I'm going to solve this equation for my final height, my delta y. I know my final velocity is 0 at the peak. I'm going to add over my 2g delta y to the other side. So I'm going to get 2g delta y is equal to vy I squared. Plugging in our symbols, I'm going to get 2g, and then this is final minus initial, h minus 0 equals to just v squared. And so that is just going to give me 2gh equals to v squared. And to solve for the height, I'm going to just divide by 2g. So I'm looking to see how this height changes. So my final equation is this, h equals to v squared over 2g. In order to find out the factor by which the height changes, we're going to solve for h prime over h. Now, what h prime represents is this adjusted scenario. And here's what that looks like. H prime is going to account for the adjustments that we're making to the initial conditions, being the speed at which the object's being thrown up at. So this is 4v squared. So this initial speed has been quadrupled, divided by 2g, and then we're dividing it by h, the original, v squared over 2g. Now to simplify this, we need to multiply by the reciprocal. So here I'm going to get 2g over v squared to then get rid of this. What I'm going to get is, when I expand this, is for these two to cancel. And then to expand the numerator, I'm going to get 16v squared over v squared. And so what that means is that the ratio h prime over h is equal to 16, because the 16 is left over. The answer is already given to you here, because when I multiply the original height h to both sides, that means h prime, this new height with the adjustments made, is equal to 16 times the original height, letter D. So these problems are a bit different, but all that you need to do is find the equation that describes the motion, just like the way we would normally solve kinematic problems. But what you do in these types is that you're finding the ratio h, or the ratio of some variable prime divided by the original variable. And you're looking specifically for a number that describes how it changes. The next one reads, in order to train to fight Vegeta, Goku trains on King Kai's planet, a planet with 10 times Earth's gravity, meaning the planet has an acceleration due to gravity of 10g. Goku drops a Dragon Ball on King Kai's planet, and the Dragon Ball falls a height h in 1 second. How long or how far would the same Dragon Ball fall in 1 second on Earth? So there's a lot going on, not too many numbers. So I know that I'm going to have to follow a procedure that's similar to the previous example. The way that we always begin is to first set up our knowns and unknowns. So here's what I know. Goku is dropping a Dragon Ball. Anything that is dropped in the air has an acceleration of -g. But in this case, the acceleration is -10g because the gravity is 10 times greater. And because it's dropped, my initial velocity is 0. I know that the displacement is -h because that's the height that it falls downward. And it does all of that in a time interval 1 second. And what I'm looking for is how that displacement changes whenever we repeat this scenario on Earth. So again, whenever you have examples like this, you first set up your knowns and unknowns. Next, we're going to find an equation that connects all of these variables. So here I have an acceleration, an initial velocity, a time, and a displacement, and that's going to bring us to this equation. Now, I'm going to plug in the values for my variables, and then I'm going to find an expression for h. So I know my delta y is -h. My vyi is 0, so this entire term is going to cancel. And here I'm going to get -5g, and then my delta t squared is just going to cancel because it's just 1. Or it's not that it cancels, but it just disappears because here I just have 1 square second, but that's not going to adjust anything here. So because I have negatives on both sides, I can just write it as h equals to 5g. Now, so in order to find how far this Dragon Ball is going to fall in 1 second on Earth, I need to find this value h prime over h. H prime is going to represent my changed situation, and h is going to represent my original one, which is on King Kai's planet. So h prime, I'm dropping this same Dragon Ball back on Earth. So I know that this 5g needs to be divided by 10 so that I can adjust back to the gravity on Earth. So the h prime is going to be 5g divided by 10 divided by, here we're just getting 5g over 1. So to simplify this, I'm going to multiply by the reciprocal, 1 over 5g. I get 5g to cancel, and the ratio is equal to just 1/10. Writing it on the side here, h prime over h is equal to 1/10. To find what this new height would be, I'm going to multiply h to both sides. And what this tells me is that the height that's fallen by the Dragon Ball on Earth is 1/10 of the original height on King Kai's planet. That brings me to letter D, h over 10. Number 9 reads, a cat starts at position x equals -5 as shown. The cat is initially at rest. He runs with a constant speed 2x equals +5. Which of the following sets of kinematic graphs best describe his position, velocity, and acceleration as functions of time? So let's identify some key things about the graphs. And the first big thing I need to notice is that this cat is moving at a constant speed. Constant speed means that acceleration is equal to 0. If I look at letter A, this acceleration is non-zero, so it's automatically incorrect. Same for letter B, this acceleration is non-zero, so it is automatically incorrect. If I compare C and D, they both have accelerations that are 0, so they both check out. So next, I need to jump to my velocity time graphs. Both of these show acceleration is 0, so I need that to be represented on the velocity time graphs. This means I have acceleration, but this represents that my acceleration is 0. Therefore, I'm going to go with letter D. This set of graphs is going to best represent the motion of the cat. And the only idea I used was that the acceleration must be 0 because the cat is moving with constant speed. The next one reads, the graph below shows the velocity v as a function of time t for a 1 kilogram object traveling in a straight line. Which of the following correctly ranks the displacement, delta x, for the 3 labeled segments of the object's motion? If I'm being asked about displacement, and I'm given a velocity versus time graph, the key idea I'm using to solve this is that the area is equal to my displacement. So I need to calculate the areas under each line segment and compare them. So here's how we do that. So for line segment 1, this is going to be my border here. And so this is going to be my area for segment 1. For segment 2, it's going to start and stop right here. Essentially, these are my barriers in red. The areas that I'm calculating for each segment is shaded in green. And so I just need to compare them. Obviously, I can compare them just by looking at them. I can visually compare that the area under segment 3 is much larger than the area of segment 2. So therefore, I know that delta x3 is greater than delta x2. Now, when I compare the displacement for number 2 versus 1, I can immediately tell that number 1 is also lesser than number 2. And that looks like letter A. If you wanted to, you could actually calculate the areas by using the areas for triangles and for rectangles, finding the base and the heights, and you could perform it that way as well. Number 11 reads, the graph provided is a velocity versus time graph for a thing that can move and is indeed moving. Which of the following is true about the speed of the object during the time interval from 0 to 8 seconds? So it wants me to select an answer based off of what's happening with the speed. So let me read the graph first and then choose an answer choice that best matches. At the beginning of the motion, I start at -2. As I come across this line, what I see happening is that my velocity is heading closer to 0. Whenever your velocity is getting closer to 0, you are slowing down. So that means from t equals 0 all the way to t equals 3 seconds, my object is slowing down. So it first decreases. It does not first increase, and it does not increase during the entire interval. And it's not remaining the same either. So immediately, letter D is my answer. If we wanted to continue reading, from 0, then as I start traveling upwards, look what happens to my values. I go from 0 and I'm getting greater. I'm moving away from 0. If my values of the velocity are moving away from 0, I am speeding up. And that's what's happening past 3 seconds. The main idea, if my values for velocity are going towards 0, I'm slowing. If they're moving away from 0, I am speeding up. Number 12 reads, the graph above shows velocity versus time for an object moving. Which of the following is a possible position versus time graph for the object? Now, there's some key identifiers on this velocity time graph. The first is that it has a constant positive velocity to begin with. Constant positive velocity on a position versus time graph will look like this. So I need my graphs to start with a shape that looks like that. So I can cancel out letter A and cancel out letter B. Now, is my shape going to look like this, or is it going to have something a little crazier looking like that? Well, another thing to notice is that I have a flat section again at the very end. And this will represent constant negative velocity, which looks like this on a graph. And that section looks a lot like this one right here in letter C. Not like this, because that's positive velocity, because that is positive velocity, but I have negative velocity at the very end. Therefore, letter C is going to be my answer. Number 13 reads, given the graph of the velocity versus time of a penguin flying due south for the winter, at what point did the penguin stop its forward motion? The key idea here is how to read a velocity time graph. If you are above the time axis or the x-axis, you are moving in the positive direction. It does not matter if you're moving along these squiggly lines, up, down. It does not matter at all. As long as the shape of the graph is above the x, you're moving forward. The lower you go just means the slower you are moving. This could be just 1 meter per second. This could be 2, and this one could be 500. But as long as you are above 0, you're moving forward because all of these are positive. Remember, the sign of the velocity indicates the direction of motion. So the penguin will stop moving forward when it crosses into the negative values on the y-axis. And so that would be at letter D. Number 14 reads, in which of the following cases would an airplane have an eastward acceleration? A says the plane travels eastward at a constant speed. Well, constant speed means acceleration is 0, so we cannot include that. That's not an answer choice. Letter B reads, the airplane travels westward and slows down. So if the plane is traveling westward, that means that is the direction of the velocity. And if it's slowing down, the acceleration must point the opposite way. And so the right was what we would call east, so therefore letter B would be our answer. C would be incorrect because the plane travels westward and then speeds up. So if my object is speeding up, then the direction of v and a are the same. So therefore acceleration would be westward, which makes it incorrect. And letter D, the airplane travels eastward and slows down. So if I'm going eastward, the direction of the velocity is towards the right, but if I'm slowing down, the direction of the acceleration must be opposite, which is west. So that just helps to show that letter B is the correct choice here. Number 15. Refer to the graph below which plots velocity versus time for a ball on a ramp. At which point is that speed of the ball equal to its speed at A? Notice we're given a graph of velocity versus time. So each of my readings on the y-axis is going to include a direction. So I'm looking specifically at point A. Point A, I'm going to say has 2 units. So and when I'm dealing with velocity, I can call this -2. But I'm looking for the point on this graph where the speed is the same. So I'm just looking for another number of 2. Well, here I have another number 2 right there. And that corresponds with letter E. So letter E would be, or point E would indicate to letter C as being the correct choice. Here we come to part 2 where we have free response questions. Number 16 reads, ball A is thrown directly upwards out a window. Ball B is dropped out the same window. Part A of this question is asking, sketch a graph of the velocity versus time for ball A and for ball B. Here's the key concept. Because we have an object thrown outside of a window, the object is experiencing free fall. And the acceleration of an object in free fall is always negative 9.8 meters per second squared. That just means that the slope of my line is going to be negative 9.8. It must always be that. Doesn't matter if I throw it up, throw it down, or if I drop it, the slope will always be negative 9.8 for free fall on Earth. Now, in in graph I, I'm looking for ball A, and ball A is thrown directly upwards. If it's thrown upwards, I'm giving it an initial positive velocity. Well, all that we would have to do to adjust for this is to shift this graph upward at some positive value. I just need to make sure that the starting point or the y-intercept on the graph has an initial positive value, but the slope will remain the same because that object is in free fall. Part II wants me to draw the graph of ball B. Now ball B is dropped, so starting from 0, I just have a slope of negative 9.8, and that would be it. Part B reads, a student claims both balls have the same acceleration, so they both hit the ground at the same speed. What, if anything, is wrong with the student's statement? Explain why the student is correct or incorrect. Justify your answer in a single sentence. So a possible response would sound like this. The student is incorrect about the balls hitting the ground at the same speed. The balls do not hit the ground at the same speed because the ball thrown upward has a greater time to accelerate, therefore resulting in a larger final speed. And that would be the answer for part B. Number 17 reads, rather than studying for physics, Brian decides to throw a stapler upwards at an initial speed of 30 meters per second. Part A asks, find the time or times when the stapler is 30 feet above Brian. It might be easy to confuse, oh, the rate is 30 meters per second, so in 1 second it's going to travel 30 meters. But you need to be careful and read that this is asking for 30 feet. Well, I can quickly convert 30 feet into meters. So it's going to be 30 feet multiplied by my conversion factor. 1 foot is 12 inches to cancel out the unit of feet. 1 inch is 2.54 centimeters. That cancels out the inches. I know that 100 centimeters is equivalent to 1 meter. Now I have everything I need to convert into meters. And that's going to give me around 9.1 meters. So I know that now. So my question is really asking, at what time is the stapler 9.1 meters above Brian? Well, that's going to happen at 2 points. So really early on, that's where it's going to happen. And it's going to happen at the exact same spot back on the way down. So I should have 2 points where the height above Brian is 9.1. But I need to find the times there. So let's go ahead and create some knowns and unknowns. Since the stapler is being thrown upwards, I have my AY to be negative G. My initial vertical velocity is 30 meters per second. I'm looking for the specific final height of 9.1 meters. I'm going to set my initial height to be 0, and I'm looking for the time or times at which this happens. So putting everything together, I'm going to get this equation. I know that the initial height is 0, and I'm going to go ahead and plug in my numbers because since my VYI is non-zero, I'm going to have to use the quadratic formula for this scenario. So plugging everything in, I'm going to get 9.1 equals 30t minus 4.9t squared. Again, I'm not writing the units and I'm not writing the deltas, just so that it makes this a little bit easier to see. So I'm going to subtract 9.1 to both sides, and then I'm going to rewrite it in order from highest degree to lowest, the way we usually do it in your math classes. So I'm going to get negative 4.9 t squared plus 30t minus 9.1. So here in my quadratic equation, a is going to be negative 4.9, b is going to be 30, and c is going to be negative 9.1. So the value of t is going to be equal to negative b, which is negative 30, plus or minus the square root of b squared, so I'm going to get 30 squared, minus to 4 times a, which is negative 4.9, times c, which is negative 9.1. All of that divided by 2 times a. And my 4.9 came from taking half of g, so when I multiply by 2, it just goes back to g, negative 9.8. Now, when I simplify what's under the radical, I'm going to get a t1 value to be negative 30 plus the square root of 721.64, all divided by negative 9.8. Likewise, I'm going to get a value t2 being negative 30, but minus this time. The square root is 721.64, all divided by negative 9.8. In the calculator, when I calculate for t1, I'm going to get 0.32 seconds. And that makes sense. Very early on into the motion, the stapler has reached a height of 9.1 meters above Brian. And so I'm looking for the very beginning, which that makes sense. I'm also looking for the very end, so much later. And the calculator for t2 is going to give me 5.85 seconds, which makes a lot of sense. Sorry, this is just 5.8 seconds, not 5.85. That'll complete part A. Part B says, as the stapler is traveling downwards, it hits the roof of the Jupiter lighthouse, which is 25 meters above the ground. Find the speed with which the stapler hits the roof. Here, let me create some knowns and unknowns once again. The question's asking me for the speed at which it hits the roof. So it's just the magnitude of this final velocity. I know that the acceleration is negative g. The initial velocity was 30 meters per second. This final height that I'm looking at is 25 meters above the ground. And my initial height I'm going to call 0. So given these knowns and unknowns, I'm going to use this equation to set everything up. To solve for the final velocity, I'm going to take the square root of both sides and add a plus or minus. So my vyf is going to be plus or minus the square root of vyi squared minus 2g delta y. And all I'm going to do is plug in my values. So my initial velocity, that is 30 meters per second squared minus 2 times gravity times my height, which is 25 meters. So in the calculator, I'm going to get plus or minus 20.2 meters per second. But which velocity makes sense, the positive version or the negative version? Well, I have my stapler, it rises up and it's falling down. So as it's going to hit the lighthouse, it's traveling downwards, which means that the velocity is actually negative. But remember, it's just asking for the speed. So the speed is just going to be the number itself, 20.2 meters per second. Part C says, at what part of its path does the stapler have its minimum velocity? And no need to justify. And the second part of C says, at what point of its path does the stapler have its minimum speed? So looking for minimum velocity and minimum speed. So the key concept about an object being thrown into the air is that as it rises, it slows. So it gets slower and slower and slower until the lowest point or the lowest speed is actually at the peak. That's where the velocity is 0. And then as soon as it goes past this peak, it's going to start accelerating. It's going to start speeding up. And so the answer for both parts is actually at the peak. That's where you'll find the lowest velocity and the lowest speed. Part D says, suppose that Brian had instead thrown the stapler up at 60 meters per second, double the speed from before. How would the time in which the stapler is in the air compare? Would it increase, decrease, or remain the same? If it's moving faster, the time is not going to decrease, and it's not going to remain the same. It's obviously going to increase. So a potential answer we could say is the time in the air would increase because it would take longer for gravity to slow the initial velocity to 0, making the first half of the trip longer. The second part reads, how would the displacement of the stapler compare? Increase, decrease, remain the same. If it has a higher initial velocity, its displacement will also increase. So a potential answer would be the displacement would increase because it covers more distance each second compared to being thrown at 30 meters per second. And that'll complete part 2. Number 18 says the displacement versus time for a panda is given in the graph on the right. What is the average speed of the panda in the 10 seconds? Hint, distance over time. So that would be average speed. Your average speed is going to be the distance that is covered over the time interval. So what would be the distance traveled? Starting from 0, we travel 1, 2, 3 meters, and we stopped at 3, and then we travel back down 4, 5, 6, 7, 8, 9. So we travel a total of 9 meters, and we do that in a total from 0 to 10 seconds. So the average speed would be 0.9 meters per second. Part B wants us to fill out the velocity versus time graph. To fill out the velocity versus time graph, I can identify some easy points to graph. One of them would be from 3 to 5, where the velocity is 0 because the panda is stationary. So from 3 to 5, I'm going to have a graph at 0. Another easy part is from 0 to 2 because I have a constant velocity. The slope is 1 over 1. So I have a constant velocity of 1 meter per second for the first 2 seconds. I'm going to save the curvy parts for last. The next easiest part is from 6 to 8. Because starting from 6, I have a negative velocity and I have a slope of 1, 2. I rise 2, run 1. So my slope is -2 from 6 to 8. Lastly, from 8 to 10 seconds, I have a slope of rise 1 and I run 2. So that's 1/2 and it's positive. So from 8 to 10, it's half. And I'm going to get a jump here. Now, the last parts are these curvy sections. So this would be slowing down. Remember how we understand these parts of a position time graph, the curvy lines. Remember, this is slowing and this is speeding up. This is slowing because it gets flatter, and this is speeding up because it gets steeper. As we start from here, it's very flat. The tangent lines get much, much steeper. Here, the tangent lines begin very, very steep, and then as we progress around the curve, it gets flatter and flatter. This section speeding up because it starts flat, and then it gradually gets steeper and steeper and steeper. And this is slowing because it begins steep, and then as we follow the tangent lines, they get less and less steep. Okay, so this section right here actually comes here, and it gets less and less steep. It matches this part. So I know it's slowing. That means the velocity must be getting lower. So I'm just going to approximate it like that. Now here, this part matches this section of the circle. And so that is going to be speeding up. And so it's going to go from here, and the velocity is going to grow. And that would complete my velocity versus time graph. Part C asks me to determine an interval when the panda is at rest. Well, the panda is only at rest from t equals 3 seconds to t equals 5 seconds. Second question says, during which interval is the speed of the panda a maximum? Remember, speed, that doesn't care about positive or negative. And the greatest number the panda achieves is 2. And that occurs from t equals 6 seconds to t equals 8 seconds. Part C says, determine an interval when panda has non-zero acceleration. Well, there are 2 sections where we actually have an acceleration, between 2 to 3 and 5 to 6. So this is between t equals 2 seconds to t equals 3, and t equals 5 to t equals 6 seconds. Those are the only 2 time intervals in which the panda has an acceleration that is not 0, because the rest is just constantly 0. Here we have a bonus. It says a baseball is dropped off a building 150 meters high. Let's picture this. Baseball is dropped. The building is 150 meters high. How fast downward should a second baseball be thrown downward 3 seconds later so that both baseballs hit the ground at the same time? This may sound confusing at first, but what's really happening is that there's a time limitation for the second ball. So I can first figure out how much time it takes for the drop ball, the first one, to hit the ground. And then the second baseball is going to have that amount of time minus 3 seconds in order to fall. And that's what's going to help me solve this problem. So let's set up our knowns and unknowns real quick. I know that my acceleration is -g. I know that my initial vertical velocity is 0. I know that the displacement is -150 meters. And I'm looking for how much time it takes for this ball to hit the ground, because that is what sets up the constraint for the second ball. So to find the time, I'm going to use this formula. My Vyi is 0, so this term is going to cancel. Therefore, I'm going to get... Here I'm going to do 2 things at once. I'm going to multiply by -2 on both sides to cancel out the negative, and then the 1/2. And then at the same time, I'm going to divide by g. So altogether, I'm going to get that my time interval squared is going to go to -2 delta y over g. Then to solve for the time, I'm going to take the square root on both sides. So my time interval is going to be -2 delta y over g. Plugging in my values, I'm going to get -2 times -150 meters divided by 9.8 meters per second squared. Therefore, I'm going to get a time interval of 5.5 seconds. So the drop ball takes 5.5 seconds. The second ball is being thrown 3 seconds later. So 5.5 seconds minus 3 seconds means the second ball has only 2.5 seconds to hit the ground at the same time as well. Well, the second ball only has 2.5 seconds to hit the ground. So I can write out my information for the second ball. So the second ball has the same acceleration. I'm looking for my initial vertical velocity. The time interval is 2.5 seconds that it has to fall, and it's covering the same vertical displacement of negative 150 meters. So I'm going to use the same equation, but this time I'm going to solve for the VYI, and that looks like this. So here, since I'm solving for VYI, I'm going to add this entire term over to the other side. I add it to the right, I can add it to the left. So on the left-hand side, I'm going to get delta y plus 1/2 g delta t squared. And on the right-hand side, that's just equal to VYI delta t. Then to solve for the initial velocity, I'm just going to divide the time on both sides, and that's it. I can now lastly plug in my numbers. So the final form of this equation looks like this. Finally, let me plug in my numbers. My delta y is negative 150 meters, and I'm adding half of 9.8 meters per second squared. And then I'm multiplying by this delta t, 2.5 seconds squared. And then all I'm doing is I'm dividing by 2.5 seconds. This is a problem for my calculator to work through. And the calculator is going to tell me that the initial velocity that the second ball must have is negative 47.8 meters per second. That's how fast the second ball must be thrown at in order to hit the ground at the same time as the first ball. So this completes the test review. This is the first practice test. I hope this helps you to understand the problem solving process, how to correctly apply the physics principles that we have learned so far. Give this video a like if it helped, and consider subscribing to the channel. Thank you so much for being a part of the College Physics series, and I will see you in the next lesson.